you're probably already aware that there are strong acids that can burn you if you touch them, and there are weak acids that are not a problem. But you may not be aware how they're different. And this is supposed to be a depiction of a strong acid. With a strong acid, the hydroxy groups, the hydrogen groups, these little protons, are all separate. None of them are with the big blue blob. In a weak acid, these are together. And there are only two that are dissociated. The rest of these are all together. So that's the difference between a strong and a weak acid. Strong acids dissociate completely. And weak acids dissociate only a little. So we have examples of strong or weak acids: hydroiodic acid, hydrobromic acid, perchloric acid are all very, very strong acids. The ones we frequently see in lab are hydrochloric, sulfuric, and nitric. Weak acids are the acids like acetic acid, which is vinegar, carbonic acid, the ammonium ion, bicarbonate ion, and water is also considered to be a weak acid. Our question down here is, why is carbonic acid a diprotic acid? Well, let's look at the word diprotic. Di means two, and protic is for a proton. Well, a proton is just a hydrogen ion. And so we're looking for our carbonic acid right up here. You'll notice it's got two hydrogens that it can lose. It can start as carbonic acid. It can lose a proton and become bicarbonate. And then it can lose another proton. So it can lose two protons, that's why it's diprotic. So bases. Strong bases also completely dissociate into hydroxy and an ion. And weak bases dissociate incompletely. You can also say that weak bases are poor hydrogen ion acceptors. So let's look at some examples of strong and weak bases. Lithium hydroxide, sodium hydroxide, and potassium hydroxide are all very strong bases. Ammonia would be an example of a weak base. Table like this one. And on this table, we've got the strong acids here. And on the other side, we've got the conjugate bases. So we have the strong acid, hydroiodic acid, and its conjugate base, the iodine ion. Notice that the iodine ion is a weak base. So a strong acid will be combined with a weak base. At the bottom of the table, we have our weak acids, like water, combined with a strong base, like the hydroxy ion. I guess I better put acid over here, just so it's not confusion. All right, so identify the stronger acid in each pair. Or maybe you want to stop the video right here. So in each case, to identify the stronger acid, we're looking for the acid that's higher on the list. So if we start with the hydrobromic and the nitrous acid, the ones in green here, you see that the hydrobromic one is higher, and so it is the stronger acid. And of these two, the phosphoric acid and the hydrogen sulfate ion, the hydrogen sulfate ion is higher on the table, and so it's a stronger acid. If we look at the hydrocyanic acid and the carbonic acid, both in blue, we'll see that the carbonic acid is higher on the list, and so we'd expect it to be the higher acid, the stronger acid. In this table, we're asked to identify the weaker acid in each pair. So you may want to stop the tape here and look these up and then go on. So in this case, we're asked to find the weaker acid. So we're looking for the one that's lower on the table. These would be our correct answers. So I mentioned this before, but strong acids have weak conjugate bases. So if you look at this table up here, you'll see that the very strongest acid has the very strongest acid on this side has the very weakest conjugate base. Weak acids will have very strong conjugate bases. Sorry. So a weak acid, like water, will have a strong base as its conjugate. If we have an acid-base reaction, which side of the reaction is favored? Which side is it going to, which product is going to be produced? What's going to be in the reaction vessel? The side with the weaker or the stronger acid? So it's the side with the weaker acid is favored. So let's predict whether the following reactions will contain mostly reactants or mostly products. So this is going to be a multi-step process. We're going to predict whether we're going to end up with reactants or products. We're going to be predicting whether we're going to make carbonic acid or whether we're going to make this hydronium acid. This is our acid. This is our base. This, therefore, is our conjugate base and our conjugate acid. We need to look on our table and see which acid is stronger. So if we look on the table, we're looking for carbonic acid and hydronium. Let's see if we can find the hydronium ion is right here, and carbonic acid is down here. So the hydronium ion is a stronger acid. And so we will make more of the weaker acid is favored. So we're going to make the carbonic acid. Which is the H2SO3. Okay, so let's look at the next one. First, we needed to figure out which are the acids and which are the bases. We see here that we have an ammonium ion that loses its proton, so this must be an acid. That makes this a base, the water. So this will be our conjugate acid, and this will be our conjugate base. We want to compare the two acids and see which one is stronger. We've got an ammonium ion and we've got a hydronium ion. So let's go back to our table and see if we can figure which one is stronger. here's our ammonium ion here, and the hydronium is up here. So the ammonium ion is weaker, and this one is stronger. And so the reaction will go in this direction to make the weaker. And we will make more of the ammonium ion. So let's look at one more, our very last one. So here we have nitrous is our acid. Our other acid, our conjugate acid, is going to be this ammonium ion. We look at our table to see which one is higher. We will see that the ammonium ion is weaker. And so the reaction will go toward the weaker acid.